All right. Hello, everyone. My name is Alex Ferencic. I am a postdoctoral researcher at UC San Diego, and I work with FPGAs and data center networking. So let's see. Today I have a number of things planned. So first, let's see. First, I have some announcements, which I'll get to in a minute. Let's see. Second, I'm going to do kind of an overview of how firmware updates work in Corundum, just how that's implemented, what all the pieces are, how they work together. Yeah, should be interesting. And then finally, we're going to get a little hands-on. I'm going to go ahead and demonstrate how this works. And I actually have a whole stack of FPGA boards here. Let me see. These guys are going to be going into servers in the CSE machine room at UCSD. I have a whole box of these guys, and these all need to be flashed with Corundum. So I got 10 boards here, and the plan is to do a race, basically. I'm going to load one of those with Vivado via indirect JTAG, and the other 9 via the the firmware update mechanism in Corundum, and we'll see which one's faster. Should be interesting. All right, so on to the announcements. Let's see, I got 2 announcements. The first one is I recently set up a Patreon. So if you like what I do, in terms of the streams or the open source code or whatever, if you're an FPGA fanatic, feel free to support me on there. It would be appreciated. The second announcement concerns kind of the future of Corundum. So let's see, we published Corundum. Well, we first announced Corundum at the OPSIS workshop at SIGCOMM in 2019. Right, yeah, so that was about 2 years ago at this point. And then in last year, in May, we published it at FCCM. So at this point, it makes sense to kind of think about the future direction of the project. So I have the first ever Corundum developer meeting that I'm working on scheduling. And that's going to be probably 2 weeks from now. We're working on figuring out the last of the logistics and whatnot. If that's something that interests you, I got some information down in the right in the description. So take a look at that and get on the mailing list, because I will be sending around some more information about that. The gist of it, I guess I can put up the block diagram here really quick. Let's see here. All right, so this is the block diagram that I kind of put together. The idea is to do a couple of things. One of them is that we're going to bring support for RDMA to Corundum. And RDMA is a protocol that's used that's becoming more common, at least in data centers, for low latency and low overhead communication. So having that capability in Corundum would be, a super useful feature. Additionally, we're going to add an application section, so you can run, more complex applications directly, on the NIC. You'll have access to the RDMA stack. You'll have access to the network. You'll have access to, on-card RAM, access to host memory, all sorts of stuff. So you can use that for offloading, various applications onto the NIC. So lots of interesting stuff planned. Some of the stuff I have time to work on. Some of the stuff is going to require, a team effort. So if you're potentially interested in helping build some of this, please try to attend the meeting in a couple of weeks. So again, I got a couple links in the description. You can take a look at that and hop on the mailing list to get more information about the meeting. All right. So switch cameras here. All right. So now on to the main topic for today, firmware update support in Corundum. So before I get into the the technical details, allow me to provide a little bit of background just for context. So the group that I'm in at UCSD, we work on data center networking, and more specifically optical switching in a data center networking in a data center environment. Whenever you're doing networking research, you kind of have to build networks at a certain minimum size in order to see some of the network effects. So we're talking things like congestion and contention and things like that, things that occur in large networks. So if you just have, like, 4 computers or something, you're not going to see these effects. You have to build a system that's large enough in order to actually see these effects. Ultimately, you can do simulation and whatnot to get some idea of what's going on, but if you're running a data center, you're not so much interested in what the network is doing, you're interested in what your applications are doing. So ideally, what we want to be able to do is run applications over some of these experimental networks to get an idea how they perform. Let's see. And we want to be able to do that, again, at a reasonable scale. And in order to work with the experimental optical switches, we need some features out of the NICs that are, not exactly standard. So the main thing that we need is the ability to very precisely control when data is sent into the network, because the optical switches, they operate on the level of links. They make and they break connections. They don't switch individual packets. So commercial networking hardware, I don't have a commercial NIC handy to indicate with, but whatever, they aren't designed with that sort of operation in mind. They're designed for, fire and forget. They just send packets whenever, they go out over the network, and the packet switches deal with them. But if we want to use an optical switch, we need to very precisely control when packets are sent such that they pass through the switch when it's in the appropriate configuration. So we've tried for years at UCSD, despite building some of these networks using some of these high-speed switches, we haven't had a good way of controlling that flow of information out of the hosts. We've tried a bunch of different solutions, but nothing has really provided very good performance. Now we know we can do this kind of stuff with an FPGA, but it's not exactly a trivial thing to do, because there, at least until I built Corundum, there wasn't really any reference design that we could build on top of to add this kind of capability to. So a few years ago, I thought, okay, we've tried to do this in software, hasn't really worked. Is there a way we can do this in hardware and actually run it at a reasonable scale? So we had a bunch of computers, something like 72 servers from some of the previous experiments that we'd done. So my idea was, okay, let's take these servers and let's outfit them with a bunch of FPGA-based NICs and, run actual applications over this, maybe emulate the switch. But, the key point is that we need all of these programmable NICs. We'd actually looked into this previously, doing something along these lines with FPGAs and hosts, and we bought a couple of these Brasic DE5 net FPGA boards. They were very expensive, like $8,000 or something like that. With a board that expensive, it's hard to build a large-scale network. So for this project, we would need something lower cost. And after doing some searching, this was the board that we found. So this is it's made by a company called Exablaze. It's an Exanik X10 card. Now, Exablaze makes these for HFT applications. So they have their own firmware that runs on here that basically provides a pretty low latency NIC, and they also have an SDK that you can add your own application logic to. But the great thing is these cards are only like $1,200. So buying 64 of them, I mean, while not a walk in the park, it's in the realm of possibility. So we got a couple of these to start playing around with. And one thing that became immediately clear is that these boards are, shall we say, Spartan. There's very little on here, right? You got the Kintex UltraScale FPGA here. You got PCIe Gen 3x8. You've got a pair of SFP Plus modules. There's a card edge connector for JTAG here. There's a configuration flash. And there's some power supplies, some LEDs, and that's it. There's no USB JTAG on here like you have on a lot of other boards. So it's like on this board here, there's a USB connector on the back. Actually, there's one here and there's one here. You can use one or the other. And there's a module on here that interfaces with Vivado, so you can load a design directly onto the FPGA. So something like this, super convenient. You can load these up on all the servers and then just jumper all the USB ports, and everything works. But for this, we don't have that. So if we were going to get 64 of these, we'd have to make 64, custom cables. We'd have to get 64 JTAG boxes, all that would have to get, installed inside the servers. It would be a nightmare. So we needed, a more reasonable solution for updating the firmware on these things so we can actually run our experiments. And what it comes down to on these boards is you basically just have two interfaces, right? You got PCI Express or you got Ethernet. Updating the firmware over Ethernet doesn't really make a lot of sense. So that leaves you with PCI Express. The other thing is that Exablaze had an open source software repository with some of their kernel code, the kernel modules, and some of their user space tools, like the firmware update tools, were all in that repository. So I spent quite a bit of time looking at that and seeing how it was designed, because I was new to a lot of this stuff, hadn't done much with PCI Express, hadn't ever implemented a firmware update scheme before. So it's like, all right, let's try and look at all of the available resources and try to put something intelligent together from that. So since we weren't going to be using their FDK, the best I could do is hope to draw a few ideas from their firmware update implementation. And the way they did it was actually pretty straightforward. I quite like their scheme a lot, and I ended up using something very, very similar in Corundum. Basically what they did is they took the flash control pins and they just directly exposed those as registers in one of the PCI Express bars. So you just bit bang it from software, basically. And the great thing about that is that it's extremely low overhead on the FPGA end. So this is a Kintex UltraScale. It's a pretty small part. You don't want to be wasting a lot of logic resources on firmware updates, because how often do you run a firmware update? On a NIC, like never. So all that would be wasted. Or even if you're doing it more often, right? You update the firmware like maybe once a day tops, right? If you're actively developing something like this. But you're going to be sending and receiving millions of packets per second. So you want to use all the logic resources on the FPGA for your application logic and for the NIC data path, and not for the firmware updates that you're running just sporadically. I have seen some other implementations that do things a little bit differently. So, for example, we're going to be doing a collaboration the collaboration is not at UCSD, but through the research group. And for that collaboration, we're going to be using some of these big honking Bitware FPGA boards with let's see, the Stratix 10 MX FPGAs. And I took a look at the Bitware reference design for these boards because I'm going to need to implement firmware updates on these as well as in Corundum. And they use a completely different approach. Basically, their firmware update tool, it reads in the file, writes it out into memory, and then points the card at it and says update the firmware, and then all the functionality lives on the card. There's advantages and disadvantages to each method, but what the Bitware card, what that setup does is it has a lot more functionality, a lot more complexity on the card side, all these logic resources that are only used for updating the firmware, and then you can't use them for your application logic. So in Corundum, I took the simpler approach of, okay, let's try to do as much of this as possible in user space, and we'll leave the we'll leave the implementation on the FPGA kind of as simple as possible. Okay, so if you're going to update the firmware on one of these, what kind of functionality do you need? So there's kind of two main things. One of them is that you have to be able to talk to the flash chip, right? So you're going to have to be able to erase, write, and then verify what you've written to the flash chip. And then you have to be able to reset the FPGA so it'll actually reload the configuration from flash. In principle, not particularly complicated, but it is somewhat device and board dependent. So all the boards that I have here have this scheme implemented in some way. This is Exynic X10. I've got a couple of the X25s. These are the same kind of idea. I guess they put the flash chip in a different spot on these guys, under the heatsink somewhere. And then I have, so both of these use the parallel flash, and then I have a couple of other boards here. This is a Silicom FPGA board, and this is Alpha Data FPGA board. Both of these use QSPI flash chips instead of the parallel flash. So this one actually has two flash chips on it with a multiplexer. So one of them is for the the user design, and the other one is for kind of a recovery design. And this one is just a dual QSPI. So now we can take a look at the code, and I can go over, what this looks like on the FPGA and what it looks like in the user space application. All right, so here is the repository. So let's first take a look at the Exynic X10 code. So one thing about the Exynic boards that's kind of interesting is I think they laid, so I don't actually have a schematic for the board for these, so this is a little bit conjecture. I think they actually wired up all the flash pins to 2 different pins on the FPGA. One of them being the dedicated configuration pin and one of them being a standard GPIO pin. Doesn't really make too much difference, but the dedicated configuration pins, you need to do a little bit more work to access. So this one is a little bit different because it doesn't have to jump through those hoops. So these are all the connections for the flash. Well, actually, this is the core logic. Here's the top level. Okay. Yeah, so here are the flash pins, right? There's the data, address, and then the control pins. Region is like an additional address bit. So those are connected to the design through, let's see, some pretty straightforward input and output buffers here. Okay, so let's see, we got the ICAP. Okay, FPGA boot, right. So this is the flash code right here. Basically, we just run everything through some flip-flops, and that's about it. You don't need to do anything more than that. I mentioned that the FPGA has to be reset to load the new firmware image, so that's what this code is right here. This is a little state machine to drive the ICAP. So the ICAP is a primitive that allows you to access kind of the configuration subsystem of the FPGA. So what you can do with this is you can shift in some commands that will cause the FPGA to reset itself, specifically the iprog command. So this sequence is just pulled directly from the Xilinx documentation, although it does take a little bit of head scratching to get it set up because you actually have to bit reverse stuff, and I don't know why it's all bit reversed, but that's the way it's built. It's kind of confusing. Anyway, the firmware update code can trigger this after updating the flash to command it to reload the design on the FPGA, so you're loading the new design that you just wrote. That's about it at the top level, kind of the interface. And then in terms of what you actually need to do to connect this to PCI Express, obviously we have the register interface that's implemented in the bar. So I'm not going to talk about that because that part's complicated. But no matter what you're doing, you're going to need that. So right here is the kind of top level register interface for the board. So this is for all of the kind of board level control and status registers. So what we need to do for flash interfacing here is basically just provide access to the various flash control registers. So in this case, we have 3 registers sitting in the PCI Express bar space. Actually, I think there's a 4th one. So this is in the right direction, and then down below we have the read code. So I mean, this just directly accesses these I/O pins. There's no magic or anything going on here. It's incredibly simple. So that's in the right direction, and then in the read direction, you got the same kind of thing. So there's a little bit of information I have here for how many address and data lines and how many sectors the flash is divided into. But yeah, this stuff is pretty straightforward. So that's for the Exynic X10. The Alpha Data board uses a slightly different flash chip. It uses a QSPI flash chip instead. Or sorry, well, that's also the Exynic, right? Okay. This is the top level for the Alpha Data board. So this one uses dual QSPI. So let's see, how is it wired up? I think it has. I don't have a schematic for this board either. One of the chips uses a dedicated configuration pins. The other one you can access through normal FPGA I/O. So these are the data lines for QSPI flash number 1, and then number 0 has to come from, let's see, where is the module? So this is, oh, here's the flash, right, okay. So these have to come through this block called the startup block. So this is how you access those dedicated configuration pins. We got the data in, data out, and the tri-state or output enable. That's the chip select, and then the clock. So those are all of the pins for QSPI 0 and also the shared clock. And then QSPI 1, those just go through normal I/O. Again, there's really not much here. You need to do a little bit of work for the tri-state buffers for QSPI 1, but that's it, besides a couple of registers. And then again, we have another ICAP instance here that you can use to reset the device. Pretty straightforward. And then when you go look at the core logic, the setup is quite similar. So if we go down here to the register interface, we've got 2 different flash chips, and I set this up so that each flash chip gets a single register in the PCI Express register space, which is really nice because you can just point the code at whichever flash chip you're working with, and you don't have to do any bit shifting or something to pull out bits from within a specific register. So again, this is in the right direction. So we're taking the right data and we're loading it into these output registers, and we're just directly controlling the pins. So this sets the data out, that sets the output enable, that sets the clock pin, that sets the chip select, and that's it. And then if we go down, we have the other pins here. Here's the flash ID, and then this one reads the input data, the output enable bit, the clock, and the chip select for both of these. Very simple. There's really not much more to it than that. Now, in terms of the user space application for this, it's this firmware update utility, mqnix firmware.c. And this does pull in a couple of additional files. So this one uses, I have a relatively rudimentary flash driver that I put together because this has to support both BPI and SPI flash. So that's what this code does. I can just go over at a high level how this works. If you're interested in how the actual bit banging is done, you can take a closer look at this. I'll just take a quick look at this for the BPI flash. But again, this stuff is pretty simple. So let's see. Because all this sits in register space, you're just performing very simple reads and writes against a block of memory that you've mapped. So you can set the address, and it's just simple. You just write the address register. If you want to read from the flash, same kind of thing. You set the OE pins correctly, and then you read twice. And this first read is a dummy read just for timing purposes. You got to make sure you have enough time for the data to stabilize. And then this one is the actual read, and then you can release the control signals. Super simple. For performing writes and whatnot, obviously it's a little bit more complicated because you have to perform various sequences. Programming flash chips it's slightly annoying, not because it's particularly complicated, but because it seems like, at least for parallel flashes, it's not very standardized. So every manufacturer has like their own set of commands that you can use. So let's see, we've got, I think in this case we have 3 different sets of commands that are supported. So there's AMD, there's Intel, and there's Micron, I think. So yeah, if you want to program one of these flashes, you actually have to go in and read some identification information from the flash, and then use that to determine which command set that you're going to use for interfacing with it. For the QSPI flash, it's more straightforward because that's more standardized. But any flash programming, you're going to have to do something like this. So this is where it gets into, if you wanted to implement this on the FPGA, this is not necessarily a non-trivial thing to do, but it's quite a bit of code to make all this stuff work. Right. Yeah, so what this ends up exposing are routines for reading, writing, and erasing, blocks of code in the flash. All right, let's see. So that's what that does. So we'll take a quick look at the firmware update utility. Again, there's not really all that much to it. We're going down, we got a bunch of kind of helper stuff. These read and write progress things are, just kind of eye candy to show you where you are in the process. Instead of just, staring at a blank screen, it'll actually show you kind of where it is in the process of reading or writing the flash. This code also has some components for interfacing with the Linux kernel and the drivers, because it has to do things like unloading the driver and poking some bits in the configuration space. So all of this stuff is just kind of code to handle that. So this one, PCIe hot reset, that will reset the card. Disable fatal error, this will prevent your server from rebooting when you reset the card. Kind of important stuff. And then this is the actual main method. So you can give it, you can point it at the device, you can point it at if you have multiple slots in the flash, you can pick which one you want to use. Reading, writing, booting is reset the FPGA and boot from flash, and then reset. You just want to reset the FPGA without reloading from flash. This one just does the PCI Express hot reset. So yeah, not that much. So yeah, once you've pointed it at the device, this one opens it up. So this one, it basically just handles the memory mapping. It's pretty straightforward, and then also reads out some identification registers. I have this packaged up as a separate call because all of the user space utilities will use that. Once it's opened it, then it has to find the PCI Express configuration space for hot resets and whatnot. So there's some code to take care of that. And then it reads out a couple of registers from the board. So the most important ones here are, let's see, the flash ID and the FPGA ID. So the flash ID, informs how many pins the flash has, what kind of flash it is. Is it a BPI or an SPI flash? And then the FPGA ID is it's just a JTAG ID for the FPGA. And the idea is with this is we can verify that the bit file or configuration file is actually targeted for the correct device. So you're not trying to load, the wrong bit file on the device. Basic sanity check. Let's see. And we got some other bookkeeping stuff. This based on the type of flash will, open up the flash devices and do some configuration. So this is, if it's an SPI flash, looks okay. Do we have two flashes? Is it a dual SPI or is it a single? If it's a BPI flash, same kind of thing. It's got to open up that flash. Let's see. Opens the flash, provides the registers, yada yada yada. Pretty straightforward. The flash configuration register. This then determines, what all of the segments look like, what their sizes are, and the offsets. Alveo boards have a weird arrangement so that we have a flash configuration just for that, because it's two segments, but it's not an even split. It's split at some oddball address. I don't know where they came up with this, but yeah. Anyway, that took a bit of head scratching to figure that one out. Well, it's in the documentation, but took a bit of head scratching to figure out I need a new ID for that. Let's see. So that's about all there is in terms of the init. And then if you want to write, then this will open up the file. So if you give it a binary file, it just opens it and reads it. If you give it a bit file, it will open it and read the headers and actually check to make sure the device is correct. Here you go. Checks the device, checks the size, and copies it into the buffer. Text files will eventually be supported. This also does some additional sanity checking. It looks for the sync word just to make sure, you actually have a valid bit file. And then it gets to the actual programming part. So, well, let's see. So this is for dual QSPI. You actually have to do a bunch of bit shuffling to generate the two segments that get loaded into each of the QSPIs. So the way I have this firmware update code set up is that it's designed to accept a bit file. So for the parallel flash, you basically program it directly. For the dual QSPI, you have to do some shuffling to make that happen. So it's one less step than having Vivado generate the memory programming files, MCS files, which are basically just text files. This one, it's smart enough to read in the bit file and then do what it needs to do. The other annoyance is that for the dual QSPI, you have 2 MCS files, which is kind of annoying because you got to put one on one and the other on the other. So modifying the code to support dealing with 2 files at the same time is, not something that I've done yet. Anyway, so once all that's loaded, then it erases the flash and then programs it and then verifies it. Pretty straightforward. And then for the BPI flash or SPI or BPI flash, if it's not a dual QSPI, then it basically just does all these operations once. So it erases the flash, writes the flash, and then verifies it. And then for readback, same kind of thing. It'll read the flashes. In this case, it reads both because it's dual QSPI, or you just read the one flash and then it writes out the file. So you could use this for, reading out what's on the board or whatever. And then after that, then we get into the, boot and reset operations. So this one is if you want to reset the device, it'll do some preparation for that. The main idea behind this is to prevent the, so we do a couple things. One, this prevents the server from rebooting. This is a problem that you run into occasionally when you have servers that are intended for data centers and whatnot, as opposed to like just a regular desktop computer. They have some additional management functionality in terms of, server management components. So there's like a, embedded computer that's on the motherboard that monitors a lot of server functions and whatnot, and it will detect things like, PCI Express devices falling off the bus. And this is an issue that I know people have run into before, is the PCI Express, you reset the FPGA, the server management components pick up on that and go, uh-oh, problem, reboot, and there's nothing you can do about it. So this function, which is up at the top, it locates the PCI Express port upstream of the device and flips a couple of bits to prevent, those events from being reported. And if they aren't reported, then the server management hardware won't detect the problem and it won't reboot the machine. Right, so we do that, and then it disconnects from the device and makes an attempt to disconnect the driver. So obviously, it's a bad idea to reset the FPGA with a driver loaded. And then it goes and triggers the well, if you ask it to reboot the FPGA and reload from flash, then it writes a magic word, feel dead, to the ID register, which then sends the command to that state machine I showed earlier to trigger the iProg via the iCat. Okay, and then it removes the PCI Express device, performs a hot reset, and then checks to see if that worked, and it triggers the rescan and then checks to see if it worked. So not all that much to it. Yeah, so at this point, let's see. I got my development machines here, and let's do a race to see which one is faster between the Vivado loading a board using indirect JTAG and the firmware update tools doing doing it in band over PCI Express. Oh, I did get a question here. The QSPI IP would be a little bit better than bit banging. I mean, yeah, I guess you could make that argument. The problem is that it's going to be more difficult to interface with the QSPI IP just from register space, right? Because, well, all right, I'll need to take a look at that. I'm not sure it's going to be all that much better, because with the QSPI IP, it's basically just 2 transfer operations per 4 bits. So yeah, obviously it would be faster, but it would be a larger overhead on the FPGA. And you're saying it's a Xilinx specific IP, so that means it only works for Xilinx FPGAs. For other devices, it wouldn't necessarily work. You might need to write your own, QSPI access IP. But to be honest, how often are you doing a firmware update? And if it takes, a few seconds longer, from my point of view, it doesn't really make that much difference. So yeah, like I said, with like the Bitware board, they do all of this fancy stuff on the board in terms of, using DMA to update the firmware and whatnot. But when it gets down to it, is it really worth doing that? For just updating the firmware, I don't think it makes sense. Now, it's a different story if you need to be able to access the flash from the FPGA for other purposes. Like if you have a soft processor on there that needs to be able to load its firmware from the flash chip, then using the QSPI IP could make a lot of sense. And if you already have it on there, then you might as well also expose it over PCI Express. But it's like if the only thing you're doing is talking to the flash over PCI Express just for updating the firmware, then I don't know. In my mind, you might as well save the logic resources and do a little bit more in the user space program. All right, so let's see here. I'm going to go ahead and start getting this set up. All right, so I've got a couple of different development machines that I'm going to use for this. Each one has, let's see, each one has 6 PCI Express slots, but only 3 of them can accept these 16-lane cards. So we're just going to be able to do 3 cards at a time in those machines, and then the last one we'll program with indirect JTAG over USB. So I have this little carrier board that I can use to power up that last card outside of the host. Wait a second. Oh, my camera's not happy here. Okay, there we go. All right, so I have this little carrier board that I can use to power a PCI Express device outside of a host. So I'll use this for the last card. This card is only designed for 8-lane cards, but I have an adapter that I made, just a cut down extender that will fit an X16 card. So we'll use that for the last one, and then I need to load up the machine with the other cards. So let's go ahead and get all these out of the boxes. The packaging for these is actually kind of nice. I've not seen stuff done like this before. Reasonably well designed. So it opens up like that, right? And then we have the card, and we have so this is a little power cable that you can use to provide additional power to the card. We got the tester port from Silicom, right? And then we have the card. And this is not shrink wrapped. You just unfold this, and then the card comes out. So yeah, that's rather convenient. And then we open this up. All right. Okay, there we go. New electronic smell. Nice. All right. So I got a few more of these to unpack, and so these have a nice USB connector right on the back, so we're going to use that. So the thing with programming these things in the servers is that it's a 2-step operation. The first thing I need to do is load the configuration into the FPGA just directly over JTAG. So not into the flash, just into the FPGA. Once the design is loaded into the FPGA, then what I can do is reboot the computer and then talk to the design over PCI Express to write the bit file into flash. So that's the idea. So for this first one, I'm going to go ahead and plug it in here, and we will connect this to Vivado in a minute, and we'll program that with Vivado. We just make sure it's all set up properly. Plug that in, power on. Yep, okay. So the card is running. All right. Got a blinking light here, meaning that it's running off of the recovery partition. Okay, cool. So that's going to work. And then I also have a USB cable over here that we'll use for that. All right, perfect. All right, let me get this out of the way for the moment, and I'm going to go ahead and load up some of the cards in the server. Well, actually, I'll leave that over here. All right. Oh boy. Slightly heavy. All right, this, I'm gonna have to find a different spot for that. Okay. All right, so let's see, I'll get that out of the way. And then I need to put 3 cards in here. Let's see, oh, and this is gonna have to go. All right, there's my screwdriver, there we go. All right, so I need 3 of these slots, 3 of the X16 slots for the cards. There we go, okay. That screw out of the way. Oh, I also need to pull these. All right. 3 screws out of here. There we go. Okay. All right, so I'm gonna get all these loaded up, and then I'm gonna start up Vivado, and we'll have a race and see which one's faster. The firmware updates from Vivado through indirect JTAG are quite slow. So yeah, it's well, we'll see how it goes. Oh, that bag is slightly torn. Come on out of there. There we go. All right. All right, card number 1. Well, I guess number 2, right? Get in there. That one didn't fit in as well as I was hoping. I think that'll work. Okay. That isn't all the way. All right, cool. There's 1. All right, let's see here. Number 2. Oops. Get that out of the way. All right. Just trying not to make this too loud for you guys. All right, there's 2. Ah, come on. There we go. All right, there's 2. And then I need 1 more. All right, so there's card number 3. Okay. There we go. Not sure why that first one is not sitting in there completely. All right, so that's 3 cards installed. There we go. Let's go ahead and take a look at the second machine here. All right, let's get this plugged in. Power and network. Okay. Okay, that's powering on. I'll also go ahead and get this USB cable plugged in for the first card. All right, excellent. Okay, second machine. All right, let's get rid of that cover. All right, same idea here. I need to pull out the Mellanox NIC. That blank. All right, dual port connect X4. All right, nice. Now, need to get 3 more of these guys. I have a whole stack of these power cables when I'm done here. right. Card number, what are we on? Number 5 now, right? All right, number 6. Okay. All right, there's another card. Okay. And this one will be number 7. All right, there we go. Let's go ahead and get that in here. And let's see. I think we're good to go there. That one didn't drop down where I thought it was going to drop down. All right, well, that's fine. That looks sufficiently connected. All right. Let me go ahead and get this machine powered on. Okay. Power and network. Just make sure that I get it in the correct network port this time. All right. So let's see here. The first thing I need to do now is fire up Vivado. Let's see. So this is the design that I'm going to load on these cards here. All right. Oops. All right. So I'm going to open up Vivado on this here. Vivado FPGA.xpr. I need 2 instances of Vivado. All right, there we go. And that's one for the JTAG indirect program, right? Remember, we're going to race. Let me get this other card set up real quick. Okay, there's that. Go ahead and get this guy plugged in. Boom. Okay. Oh, actually, I have 2 cards plugged in. How do I know which one's which? We'll start with this one then. Okay, that's turned on. All right. Okay, so auto number 1. All right, and auto number 2. Okay, cool. So that's open. So now I'm going to go ahead and open up the hardware manager here. Okay, we got 1 target. Oh, auto connect. That's what I want here. Okay. Why is it showing me 2 things? Oh, because I have the USB cable hooked up. Invalid core. Oh, it must be, maybe it's an old version of the MIG. All right, so this is definitely one of those. What do I, what's this other thing? Okay, right, so that is USB connect. This one is this guy. Okay, cool. Does this say anything about which one is which? All right, well, hopefully this is not going to be a major issue. All right, so, oh, I need to generate the Flash programming file, don't I? All right, let me do that real quick. Second, I think I have, let's see here. Oh, that's the wrong big file, this one, okay. So this is going to be, all right, let's see, I'm going to go ahead and just, yeah, all right. I usually do this with the make file, but the make file is not happy right now, so I need to go ahead and do this manually. All right, tools. Where was the command for this here? Generate memory configuration file. There we go. That's what I want. All right, so MCS custom, wait, okay, memory part. This is going to be, oops, all right. So this is an MT25QU512. All right, select this, MT25, MT25QU512. There we go. Okay, select that. 5.4, load bitstream up. Going to be FPGA.bit. Okay, I think that's right. Yep, loading from 0. Right checksum, sure. Okay, cool. So I will do that. Okay. Oh, need a file name. All right. FPGA CS. Okay, there we go. All right, there we go. Now we have that generated. Right, for these other ones, see, there we go. All right. So now what I need to do is add the configuration device, right? Again, this is the MT25QU512, right? Go. All right, select that. All right, there we go. And yes, I do want to program it. Okay. And there's the MCS. Okay, very nice. I want to erase it, program it, and verify it. All right, excellent. So, race is on. Okay, and now this is starting to program the flash via indirect JTAG. So it programs the FPGA first, and then it goes through the FPGA to access the flash. While that's running, let me load all 6 of these cards here. Okay. Let's see. I'm going to open the hardware manager. No content. Oh, open target. Right. Okay. By auto connect, is this going to work, or is this going to? Ah, man. All right. Maybe what I need to do instead is do this. Log into the machines and run Vivado on there manually. Well, I was not expecting this problem. Oops. Wow. Try to switch the view. Apologies. Okay, so we have that generated. Well, all right, this is not going to work the way I was expecting it to. Yeah, apparently. Oh, I see. What? I should be seeing a second card. Oh. All right, so that could be an issue, actually. All right, that's an unexpected problem. So apparently all of these Silicom cards have exactly the same serial number programmed into them. And I think that's tripping up Vivado. I think if it's seeing multiple cards with the same serial number, it either didn't detect that card for some reason, or it, oh boy. All right, I guess I'm just gonna have to run Vivado on that machine itself instead to resolve this issue. All right. And I will go ahead and do that then. All right. So, let's see here. Well, maybe the indirect one will win because of all these unexpected issues. UCSD projects. Okay. All right, so. Yeah, all right, so that's not happy about that. Dang, okay. That TCL script here for programming, nope. Dang it, keep running into unexpected annoyances. All right, let me manually take care of this here. This is program.tcl. All right. Actually, I guess I could. Maybe this will work. Okay. Is that going to work? All right. All right. Very cool. So I can go ahead and put in. Okay. Now I should be able to run that on the server. Yep. Okay. So I need to do Vivado. See here. Command for this here. Yeah. Okay. Run that. All right. Okay. This one should program that, and this is just loading the code only onto the FPGA. Once that's done, well, I got to do it for all 3 cards in that machine. Once that's done, then I will reboot the computer, and then the design can be loaded into Flash via PCI Express. All right, so there's one loaded. Oops. All right. Let me move it to the next card. All right. Let's see here. Let's move it over. Oh, wait. That didn't work. It didn't find the the TCL script was messed up. All right, it should be correct now. Let me try that one more time. Okay, program it. All right, there we go. I think that'll work this time. I guess these boards are actually not too bad for JTAG indirect programming because the flashes are relatively small. I just wrote a different board not too long ago that took like seriously a half an hour just to do the readback on 2 config flashes. So yeah, it's not the fastest thing ever. All right, second one. That one did work. Yes, it did. Okay, program that. There we go. All right, second one is programming. And after this, so I got to do a third one, and then after this, we'll be able to do the Flash programming on these guys. Meanwhile, let me get the other machine configured here. Yeah, all right. So that was faster than expected. All right, FPGA. All right, third card on this machine. Okay. Okay, I will do that. All right, so I gotta do the same thing here. Source that. Okay, so as soon as this is done, then I'll be able to go in and actually program these things via the in-band PCI Express technique. So, okay, that says exiting Vivado, so I think we're done. Let's see, I'm seeing the expected blinking lights on all 3 boards. So at this point, I will go ahead and reboot this guy. All right. So the reason you have to reboot is when the PCIe bar configuration changes, you have to rescan the bus. And you can only do that on reboot. Okay. So now we should be set up for the second machine here. Okay. There we go. Start the first one. All right. All right. Well, I can still do the race again, just with 6 cards after they've already been preloaded via JTAG. So, not quite as fair, but we'll see. Okay, there we go. Exiting Vavato, that's the first card. And now the second card. All right, let's see if that's rebooted. These things tend to reboot, well, they're not the fastest, but they're a lot faster than some of the servers that we have on campus. All right. Needs another minute. All right, so that's the second card there. And the third one. Okay, there we go. So now we're connected again. All right, let's see if the cards show up in LSPCI. All right, I need to get a proper PCIe vendor ID at some point. Okay, so those are the 3 cards. They are now running the Corundum design. So at this point, we can now use the firmware update tool to talk to these cards. So let's see here. Under utils, so I will make. All right. So you'll notice that I have not loaded any drivers for these cards yet. So I will prove that real quick. LSPCI, let's see, -S. Hang on a second. 01. Oh, I gotta run that under sudo. All right. Okay, so it'll indicate what the kernel module is loaded down at the bottom. But since there's no driver loaded, it doesn't say anything. Okay. So what we can do is run unique firmware, right? So this card, let's see, let's point it at the device name in this case. So we're going to use it without the driver, so we have to go locate the bar in sysfs. So that's going to be sys bus PCI, and the device ID was, PCI devices. It was 01, right? Resource 0. Oops. I need to add sudo. Okay. Hey, there we go. We can talk to the card without any firmware or without any driver loaded. So there's the card. Got the flash ID, FPGA part, right? SPI flash, data width 4. That's just 1. It's not a dual QSPI. Here's the information that was read out. It's a 64 megabyte flash. Although the slightly annoying thing is that the part numbers for these are all in terms of bits. So you might see like a 1G, but that's 1 gigabit. You got to divide by 8 to see the actual size. So this one's a 512 megabit. So that ends up being 64 megabytes. And there's one segment starting from 0, length, 64 megabytes. Okay. So with this, then we can, we go ahead and get everything loaded on the other machine. I think, did I load that last card? I think I did. 1, 2, oh, all right. Let's see here. How many times did I do this? 1, 2, 3. Okay, so I think all the cards are loaded. I will reboot that. All right, so once these guys reboot, then what I can do is we'll go ahead and do the race again then, shall we? Okay, so I'm going to connect 3 times to both of these. Okay. These 3 are looking at the first one. I'm going to have 3 on the second one. All right. All right, and then I'm going into the same folder here. Pushed the wrong button. All right, copy. All right, and then I'm going to have to do the same thing. So this is going to be, what were the device IDs that I'm interested in here? It was 01, 81, and C1. Okay, all right, so here we go. This one's set up for 01. I need to do the same thing for 81 and for C1. So 81, right? Okay, make sure that works. Oops. Resource. If I can type today. Resource 0. Okay, there's the second one, and then the third one. So C1. All right, resource 0. Okay, excellent. Okay, there we go. There we go. 1, 2, 3 cards, and then I need to wait for this guy to reboot. Hopefully that won't take much longer. All right, I'll get this set up for programming again, and you will see here. As soon as this thing finishes booting. Well, I guess I can kick this off. This will take a minute to reboot, but I think, oh, there we go. All right. All right, one more. Okay, and let's see now if I go into this directory here. Okay, copy that. All right, so I need O1, yes. Resource 0, okay. Okay, that looks good. All right, and then I need to do again, let's see, this was 8.1, right? 8.1, source 0, okay. That looks good, and one more. So C1, resource 0, okay. Very nice. All right, there we go. All right, so now I need to point these at the actual bit file. Let's see. That was FP2CQ 100G version, FPGA.bit. All right, very cool. So all these are going to get the same thing. Right. Okay. So now we can race. All right, so I'm going to go ahead and hit start here. Wait for that to program the device so we're on an even footing. Okay. And now, right, hang on a second. Okay, it's erasing the flash. All right, well, these also are going to run the erase routine, so I'm going to go ahead and start these then. Oops. Okay, first one. There we go. Erasing, writing. 30% already. Okay. Well, I think this is maybe not a completely fair comparison because if the flash is already erased, the erase operation is much faster. But anyway, yeah, it basically wrote half of the flash before the JTAG indirect was able to finish erasing. Yeah, okay, so there we go. They're all done writing, and now they are reading and verifying that what they wrote was correct. So yeah, let's see, how long does this take? Actually, we can run this under time, I guess, on one of these and see how long it takes. The other thing I can show you as well is the demessage output when the card is rebooted. All right, there we go. Bing, bing, bing. We got 2 done, 3 done, 4, 5, and all 6 are done. And how far did this get? Yeah, 17%. Right. So even bit banging QSPI, this is way faster than Vivado indirect JTAG. So yeah, that's pretty convenient. So actually, so this one I'm going to go ahead and run this under time, and we'll see how long that takes. For this one though, I'll just go ahead and reload all these and make sure they work. So what I do is I do -B, and then this triggers the iPro to reload the FPGA. And I make sure to give plenty of time for things to work. And there we go. It says device is online. So we can see it removed the PCI Express device, and then it rescanned and reassigned it. So here we go. There's the remove, and then it detects the device and assigns the bar. So there we go. And I can go ahead and reboot all of these. So that one looks good. Do this one. Well, these are on the other machine, but you know, same idea. So I can reboot that one, and I can reboot that one. All right. Oh, there we go. And it looks like I can see all of the blinking lights that I'm expecting to see. So it looks like that's running on all the boards. So perfect. All right. Let's see. Is Vivado done yet? Maybe this is a better comparison here, because this is 40% of the way through verifying, and Vivado is, you know, only halfway done with step 2 here. I guess Vivado does indicate what the elapsed time is. So the last time I ran the, oh, it's not going to let me scroll up because of this thing. All right, I'll have to wait. Hey, there we go. 2 minutes. It took 2 minutes to reflash the card, to erase, well, not the whole QSPI. I guess only where the bit file is located. But yeah, so, you know, minute and 50. That's not bad. Actually, that does raise a question. I don't know if Vivado is programming the entire flash or just the used portion of it. So I think last time I ran this and it took ages and ages in Vivado, I think I was reading out the configuration flash to do like a blank check or something. So it's got to read the entire flash to see if there's any bits set. And because it's reading the entire flash, it takes a long time. But this one didn't program anywhere near the whole flash, right? So the length goes up to, you know, 64 megabytes, hex 04, but it only wrote up to, you know, 126. So this is only a little bit more than a quarter of the flash. So yeah, I guess if you take this and you multiply this by 4, that's about 2 minutes. If you multiply it by 4, that's about 8 minutes. If you were to use the whole flash, it would take a lot longer. Well, let's see what Vivado says in terms of this, but I think if it's not programming the entire flash, then there's definitely a pretty significant difference here. All right, well, I got 3 more of these I need to load, but it's just going to be more of the same. So are there any questions or anything else? Let's see, anything else popped up in the chat here? Let's see. WB star, right, talking about ICAP, yeah. Yeah, so I guess right now I'm not doing any kind of multi-boot stuff. So yeah, that is something that you can do, is use WB star to load a different image from the flash. Obviously there's other stuff that you can do in terms of, you know, partial reconfiguration, you know, if you want to reconfigure just kind of the application section of the FPGA or whatever. That is stuff that you can do. For the time being right now with Corundum, I'm not bothering with partial reconfiguration because it there's a lot of additional logistical concerns associated with that. One of the biggest is that you just have to make sure that that the configurations that you're loading, the pieces that you're reconfiguring, are you have to make sure all of your bit files are compatible with each other, basically, right? So if you're partial reconfiguring, you can't just do that on top of a random design. It has to be on top of, you know, kind of a parent design, if you will. And so you have to keep track of all that. And if you're swapping out, you know, both the, you know, the inner portion and the outer portion, then it's just complicated from a logistical standpoint. And unless you're trying to do this like at runtime to save time or whatever, you know, it doesn't really provide a significant advantage, at least from the point of view of what we're trying to do. Okay, flash programming completed successfully. It says elapsed 7 minutes and 11 seconds. So, you know, that's not too bad. If you're accessing the entire flash, let me actually take a look at how that was configured. If I do program configuration memory device, yeah, address range configuration file only. Yeah, not the entire one. Okay, so Vivado took 7 minutes and 11 seconds to erase and reprogram just the section of the flash that we were using, right, where the file sits. And the in-band technique took, you know, 1 minute and 51. So what is that? How many times does 2 go into 7? It's you know, 3.5 times faster. That's pretty good. And I mean, yeah, obviously you could do better than that if you know, wanted to throw DMA at the problem or whatever. But when it gets down to it, do you really need to do that, right? It's, in my mind, that's basically unnecessary optimization. You could spend the time to do it, but what's the advantage really? And, you know, what's the trade-off? Because when you do that, you're going to be using more resources on the FPGA that can't be used for other things. So it may make sense just to try to do you know, everything on the you know, from user space and kind of have the smallest footprint instead of, you know, trying to do some sort of a DMA setup. And actually, speaking of that that bitware design, where they do have kind of the more advanced setup, basically it makes a lot of sense in terms of if you want to take their design and then, you know, build your own user logic on top of it. But if you want to make significant modifications to the design, such as if you want to use a custom DMA engine or something, that then presents a problem because, well, their design is dependent on using the, you know, the Intel DMA engine versus your design, you know, you want to use your own. And, you know, that's on most FPGAs, you can't really reconcile that very well. So you either would have to redesign your design such that it'll use the Intel DMA engine, or you might have to re-implement the firmware update mechanism yourself. So, yeah. Although there is another consideration as well that I have been putting a little bit of thought into. It doesn't apply maybe so much to the firmware update part of things specifically, but it could apply to a few other considerations. So one thing about Corundum is that there's a number of kind of management features. And firmware updates is one of those, but it's not the only one, right? So let me see here. There we go. Okay, so, you know, for example, on these boards, obviously being able to update the configuration flash is important, but you also have the optical modules, and these optical modules have an I2C bus going to them for configuration and monitoring and whatnot. So being able to access that, you can read like the launch and the receive optical powers and some other things. You can change some settings. You can enable, disable CDRs. There's a bunch of stuff that you can do over that I2C interface. So that's a rather important thing to make available. But every board has a slightly different way of exposing that. Additionally, if you're making a NIC, you probably want to have, you know, consistent and persistent MAC addresses, right? So on this board, there is a microcontroller on here that handles board management functions, and this microcontroller has those MAC addresses stored in it. So you have to talk to that microcontroller to read out the MAC addresses. And other boards have EEPROMs. Some of them are connected directly. Some are connected through I2C muxes. You know, this kind of stuff can be very board dependent. Now, the way you would access this stuff from, you know, user space on Linux is these guys, you will go through an ethtool API. And for the MAC addresses, you know, the driver needs that during startup when it's registering the net devices in the first place. So the driver needs to be aware of how to get this information. So one option is to bit bang it and then use like the Linux kernel I2C subsystem, which has a driver for bit-banked I2C interfaces, and use that on the driver. Perfectly valid option. But the problem is now you have board-dependent code in the kernel module. And if you're only doing out-of-tree stuff, then that's not really an issue, because you can have the smallest footprint on the board. You can put most of the functionality in the kernel module. If you need to support a new board, you just add the code to the kernel module. But if you were, say, to take that kernel module and get it upstreamed into the Linux kernel, well, now the entire calculus changes, because it now becomes much harder to change that kernel module, unless you're just going to ignore the one in the kernel. But in that case, why did you bother getting it upstreamed in the first place? So in that case, it actually may make sense to push more functionality into the FPGA design, such that you're not exposing this board-dependent stuff to the kernel, right? And to the kernel module, which is going to be more difficult to modify. So that's actually something I've been putting a little bit of thought into. Potentially down the road, it might make sense to put like a small soft core on the FPGA that can manage a couple of these functions. And potentially that could also be used to handle some of the firmware update procedures as well. Such that you could use, say, the ETH-tool firmware update API to load new firmware onto the card. Yeah, so, as a research project, as things are right now, it makes sense to try to minimize kind of what's running on the card as much as possible. But that calculus, can change depending on the applications and the details. All right, well, if there aren't any other questions, then I guess I'll go ahead and wrap up the stream for now. Thanks to everybody for tuning in, and hopefully you learned something.